PRACE provides world-leading computing facilities that are available to scientists across Europe, both in academia and in industry. PRACE goes beyond what is available nationally. It enables scientists across Europe to share national facilities, and it can procure systems that would be much too expensive for any one country to be able to afford. The other thing that PRACE does is to offer the possibility of making very large allocations of time on those systems. So that means that it's capable of supporting the most demanding and challenging scientific projects. When I was invited to chair the Scientific Steering Committee of PRACE, the Chairman of Council, Achim Bachem, said that it was his aim to put the user in the driving seat. We can be grateful to the supercomputing centers in Europe for establishing the PRACE infrastructure, but now we really need the scientific community to take responsibility for driving that infrastructure forward.
Computational plasma physics has been around almost as long as plasma physics itself, and you can go back to the 1950s where computation started playing a very important role in helping plasma physicists understand the phenomena that they were interested in. Presently, there are a number of plasma physics applications where HPC plays a key role, and most notably thermonuclear fusion research, be that magnetic fusion or laser-induced fusion. Also compact accelerators using beam plasma interactions, and also some astrophysical plasmas where HPC plays a very, very important role. The reason why HPC is so important is that these scenarios are very complex, strongly nonlinear, which makes purely theoretical descriptions impossible. And some holistic comprehension of what is going on heavily relies on HPC as a third pillar of research beyond theoretical and experimental research to really understand what is going on and what we can do from it.
Weather and climate simulation require very large supercomputers. We are amongst the largest users of supercomputing, but any science area that deals with natural hazards, this could be storms, flooding, drought, fire, windstorms, we are among the type of natural scientists that study anything that can affect human society, and we do require major amounts of modern supercomputing. In traditional climate science, we study our planet as a whole. What is actually needed in modern climate simulation is to be able to distinguish different regions, different periods of time in the climate record. We want to be able to simulate the weather and climate processes. We want to simulate things like typhoons, hurricanes, windstorms, major rainstorms, flooding events. This is like looking at climate with a very high definition camera. Very, very high memory requirements, very strong CPU requirements. This is very expensive. In order to jump to such high resolution, we need very big supercomputers.
One of the big challenges in the life sciences is modeling things across different scales and using different types of physics. When you simulate a multi-scale phenomenon that operates on different scales, you want to combine multiple simulation codes into one larger simulation. And to orchestrate these simulation codes properly and to have the boundary effects properly takes a lot of study, and especially to ramp it up to HPC infrastructures, the larger scale is quite difficult.
Astrophysics is a basic science, so its main purpose is to try to understand the origin and the evolution of the objects in the universe. And for that, its basic impact in the society is just increasing our understanding of where we are sitting in the universe. In astrophysics, HPC is a fundamental tool because astrophysics is a very special field of science. It cannot handle the objects it studies because it deals with the universe as a whole. And then the only way to do experiments in this area of science is by simulating the objects, simulating the universe in a computer. So in this case, HPC is for astrophysics is basically the laboratory of that in other branches, in other areas of science, you have labs with different instruments where you can measure things. In our case, in astrophysics, the only tool we have to do experiments is by simulating them in the computer.
The areas within computational astrophysics that I'm most familiar with would be star formation, which is the area that I concentrate in most, and also a little bit to do with high energy astrophysics. So this is the kind of thing that happens when stars die, so you get supernova blast waves, and the physics that happens there is quite complicated and involves very high energy densities and so on that we cannot reproduce with experiments on Earth. So we need to do simulations to find out how these things happen. The types of simulations that we run are so complex that the standard computational resources that a university or a research group might have just simply aren't sufficient to give us the results to an accuracy which would allow us to understand what physics is actually occurring.
PRACE allocates large amounts of time to projects through competitive peer review. So there are calls for proposals every 6 months, typically in May and November each year. And those proposals would normally be for an allocation of time over a 1-year period. It's what we call project access. But we're also introducing the possibility of applying for time for a longer period, initially perhaps for 2 years. The criteria for awarding time are scientific excellence, and in particular we're looking for projects that have the potential to make a significant step forward in knowledge, and also their suitability for using Tier 0 international level facilities in order to achieve those objectives. We try to award time only to the best projects, and then we give them all of the time that they request, or we award nothing. We also have other mechanisms for awarding small amounts of time. Particularly preparatory access allows researchers to develop their codes so that they can make efficient use of Tier 0 resources. And then that can form the basis for them applying for large allocations of time through project access. Currently, we don't implement any juste retour. So for academic research, there is no restriction on nationality. We're prepared to consider proposals from researchers anywhere in the world. And the reason we do that is that we want PRACE to support the very best science in the world. And we rely on our peer review processes, implementing best practice and selecting the very best projects. And if we're allowing the competition for access to PRACE to be worldwide, and if our processes of selecting those projects are as good as we hope they are, then we can be confident that PRACE is supporting world-leading science. To date, we've awarded large allocations of time to 60 projects involving scientists from over 20 countries. And in total, we've allocated something like 2 billion core hours of time on Tier 0 computers. The competition for the resources is fierce, so we actually receive 4 times that number of applications. The results of the work that's been done on those projects is only just now being understood by the scientists involved. But this is an area of science that is expanding rapidly. PRACE is doubling its capabilities year on year, and these are projects which are growing bigger and bigger as our capability to support them is growing. So I think we can be very confident that over the next 1 or 2 years, we're going to see in several of these areas big breakthroughs in science coming from the ability of our scientists to access these high-performance computing facilities at the very highest levels of performance.
In my case, what I'm interested in is in studying the first stages of the formation of galaxies in the universe. So for that, what we simulate is the formation, the evolution of the first structures that were forming the universe when the universe was less than 1 billion years old, and currently it is 13 billion years old. So it's when the universe was pretty young. So this is my main field of interest, and this is the project we are currently running in PRACE Infrastructures, is just to do simulations of the very first stages of galaxy formation. We have been able to finish one of the largest simulations of galaxy formation done so far, to study the early stages of galaxy formation in the universe, in which one of the main achievements is that we have combined together the two main components of the universe, the dark matter, which is invisible, I mean it's not emitting light, and the normal matter, which is usually called baryons, and they are combined in the same simulation in a sufficiently big box to do comparison with observations, and also with enough resolution to resolve the early galaxies in the universe.
The main task that I'm involved with at the moment is turbulence in regions of our galaxy that form stars. We know that these stars form in clouds of fairly dense and very cold gas and dust. And we know that these clouds are turbulent, and we know that that turbulence will influence what types of stars are formed. When we are trying to understand this type of turbulence, we can't just go and do an experiment and try and study it like that. What we need to do is computer simulations. So we do the computer simulations, and then we try to link those with the observations, so link them with the things that we see in telescopes. And the main work that I'm doing is basically extending the physics that we've been able to include in these simulations of turbulence to more realistic physics. And of course, when you extend the physics, that means you've got a higher computational cost. So we need very high power supercomputers to deal with this issue. So the main thing that we've found is, through the inclusion of the extra physics that we've been able to do, is that the turbulence in these clouds in which stars are forming will form density structures only of certain sizes. And you may say, now, why is this relevant? This is relevant really because how stars form depend completely on the kinds of density structures that you form. So exactly where all the mass in the cloud is, and is it big lumps of mass or very small lumps of mass or whatever. So the kinds of star formation that occurs depends completely on that. And it turns out that the physics that we've been able to introduce into our simulations has a very significant impact on exactly that. So we know that this extra physics, which has never been done before, does actually have critical influence over star formation, which is one of the fundamental problems in astrophysics.
We have been able to simulate some historical damage due to very powerful storms like hurricanes in ways that have never been observed before. These are types of simulations that were, even a few years ago, impossible. And we can do this for actually hundreds to thousands of years of simulation, which is not available in our observations. So in many ways, we are using the computer simulation as a synthesis of observations we've never had. To begin with, the codes that we use on the supercomputer are shared with the operational weather center, so they're used for weather prediction, for seasonal prediction, as well as for climate research. It is also true that natural catastrophes are amongst the most costly to society, and this is very important for government, but also for industry. And much of my activity deals with the insurance industry and understanding how we can reduce losses to business, to society, and also loss of life. And we do need to understand how these weather and climate phenomena are changing with time. This is crucial to our society. The types of natural phenomena that we study with the supercomputer are amongst the most dangerous and most costly ones that our society faces every year. If you look at the insurance industry that funds half of my chair, for instance, the types of storms that I study with the supercomputer are amongst the costliest to their yearly portfolio. We have a fellow embedded in industry who studies these phenomena and actually helps develop decision-making tools to understand the risk associated with these natural phenomena.
Currently I'm working on a laser acceleration of ions. This is done by shooting a very high intensity laser into a gas target, and as a result you get accelerated proton beams. The work started a long time ago where our group, through HPC, demonstrated that the acceleration mechanism was a feasible way of producing accelerated ions through laser-plasma interaction. But recently we did the modeling work for an experiment with our collaborators at UCLA, where we demonstrated the feasibility of such a system with realistic applications. The main result or results that we get from supercomputing modeling, from HPC, is a deeper understanding of a number of physical phenomena that we are interested in. And in particular, whenever you're talking about high-intensity laser plasma or laser solid interactions, it's a very complicated process with a number of things going on at the same time, which makes a pure analytical description impossible. Through that understanding, it's then possible to use HPC to try to understand how these systems can be applied in other scenarios, and to determine practical and technological applications. But again, if I had to highlight one thing, it's really the deeper understanding of a number of physical phenomena that would otherwise, not be there. The social and economical impact of thermonuclear fusion as a technology for producing energy is more or less obvious. The quest for a cleaner energy source that's free from oil dependency is one of mankind's goals, and in that sense, HPC playing a critical role in all the developments regarding thermonuclear fusion helps steer the community and all the science and engineering efforts towards this goal. On another aspect, when you're talking about, for example, these compact particle accelerators that can produce both particles and radiation that is suited for biomedical applications, these can also have a very significant impact, because these can operate at a very small fraction of the cost of present proton therapy systems. And this will, of course, make these treatments available to a much wider range of people than what is happening presently.
At the moment I work with the HemOB blood flow solver. With it we simulate blood flow in the human brain, and the idea of HemOB is to assist a surgeon eventually with surgery to prevent brain aneurysms. So to do that, we basically have to have good visualization and steering performance, and of course resolve the blood flow accurately. We are assessing that performance, but also as a follow-up to that, we are coupling the code to a code that models blood flow in the rest of the human body. So then we have a simulation where on the microscopic scale we use HemOB to simulate the brain aneurysm or the area susceptible to a brain aneurysm, and we couple it to a second code that models the remainder of the human body, at least the blood flow within that. We are testing the code. We are testing it mainly for performance and also improving the accuracy. Performance-wise, we've managed to scale up the code to 32,000 cores on the Hector supercomputer in the UK. It scales practically linear to that core count. But in addition to that, we also ran it with steering, so that means that the doctor can interact with the simulation, and visualization enabled. And we were able to attain a frame rate of about 5 frames per second with 14% overhead on the simulation. when somebody is visualizing the output and interacting with it. One of the things we also want to do is to test the code for accuracy. We are doing that, and we already improved the accuracy of the code through the past period. But to really make it usable in a clinical setting, we need to go through a full clinical validation, and that will probably take many more years. So that's an ongoing process. The results from our project using HeMel-B are quite directly relevant to society, because we plan to assist clinicians in, well, basically resolving or preventing brain aneurysms. They will be used by doctors eventually directly in surgery. So it's quite directly important, and it might save people's lives. There are a couple of conditions though to make it working properly, because when somebody is about to get a brain aneurysm, it can be a very short time before it actually takes place. So if we ever put this simulation in practice, and well, if everything goes well, we hope to do that in a number of years, then we also need to give the doctors the ability to run the simulation right away. So also computationally, we need to have things in proper place then. But if those things are in proper place and we are able to run the simulation right away without being queued, for example, then it is directly relevant for society. I think the social and economic impacts of simulations in using HeMel-B, so blood flow simulations, are quite direct. It helps surgeons get insight about their patients and about the effect of their surgery before performing the actual surgery. So aside from saving lives, it will also save a lot of money on healthcare on potentially failed surgeries. Aside from that, I think there's also a larger impact on the medical community as a whole, because using these simulations we are able to get a lot more knowledge about patients in general, also for other diseases, and use that knowledge also to validate treatments and to predict whether certain types of medication or treatment will work as intended.
Computing technology is continuing to advance very rapidly, and we can anticipate that by the end of this decade we will have exascale machines. So that is a further factor of 1,000 increase in performance of these computers. However, that step to exascale is going to be more revolutionary than evolutionary, because in order to exploit that technology, we're going to have to learn how to exploit much greater levels of parallelism. So these computers will have hundreds of millions, even billions of computational threads. Each thread will have much reduced bandwidth to memory compared with what we're used to today. And these machines are likely to suffer undetected errors much more frequently than we're used to today. So we're going to have to rewrite much of our software from scratch, and that will require a big international effort. PRACE is very well positioned to coordinate European software development to enable us to do that. PRACE has to continue to grow, and it needs to grow in partnership with the scientific community. We've demonstrated that we can cooperate across Europe in this area, and that puts us in a very strong competitive position in relation to the other countries that are big players in high-performance computing, like the USA, Japan, and China. PRACE does need to strengthen its organizational structure. It will need to create a truly European organization that can pool some of the national funding to enable it to procure these very powerful systems at the leading edge and ensure that Europe remains competitive in this important area of scientific research.